It's 3 o'clock. Shall I get started?
Maria, are you ready?
I am.
Perfect. All right. You should all see my screen. So hello, everyone. Welcome. Good afternoon for those in Europe, evening for those in Asia, and good morning to you in America. So my name is Jaap Nunes, and I'm hosting the Sources Sync seminar this week. And I'm very happy that we have Maria Santos as our speaker for today. As you can see here on the slide, she'll be presenting on social ecological aspects of Delta development globally. So I'm really looking forward to her talk. But before I'll allow her to share her screen, I want to also give the announcement that next week, same time, we have Gesine Mollenhauer present on Arctic deltas and on organic matter transport to Arctic deltas. So stay tuned for next week as well. You'll probably see announcements on Twitter and YouTube about it. So for this week, we have Maria Santos, and she's an associate professor at the University of Zurich. Before that, she did most of her education in the US, in Arizona and California, focusing on ecology of river deltas and wetlands. And she started as an assistant professor at Utrecht in 2013 and left actually, I think, just before I arrived or about the same time to take up a position in Zurich. And looking not only at ecological aspects of river deltas, but also from a sociological element. So with that, Maria, I will unshare and you can share, and I'm unmute myself. I'm very looking forward to hear your talk.
Thank you. So, first of all, good morning, afternoon, evening to all the participants. And thanks very much for the invitation to share some of the work and kind of the journey that I've been undertaking in studying delta system development from a social ecological lens. Thank you very much, Jaap, for the introduction. So with that, I will just get us started on this journey of what do we mean by social ecological lens about deltas. First of all, I would like to acknowledge many influential people to the work that I will be presenting today. And I wanted to start with the people that I worked with in California when I was there, and that will be influencing the local scale study that I will be talking about later on in this presentation. Some collaborators from the Future Deltas program at Utrecht University, where I was before joining now the University of Zurich University Research Priority Program in Global Change and Biodiversity, and the work of my PhD student, Martin Reeder. There's many more people that could fit into this slide, but I think these are the key players, and please do not feel excluded. I really appreciate everyone that has contributed to the work that I will be presenting. So it shouldn't come to a surprise to the audience in this seminar series that deltas are at risk. And they are at risk because of many reasons that have been put forward by a series of people that have been very instrumental in guiding our understanding of delta systems. Deltas are important historically and currently because they hold a large fraction of our global population. They experience very large land use changes and water extraction. They suffer from increased land subsidence, accumulated pollution. They're very vulnerable to sea level rise, floods and droughts. And they supply many nature's contributions to people, the new naming of ecosystem services, both locally, but also internationally. So today, I would like to take us on a journey about deltas at risk. So it shouldn't come to a surprise that deltas at risk because of changes in sediment flux, and that the processes that build and maintain deltas have been greatly diminished or even halted in the last centuries or more recently. 60% of delta sediment may be drowning within the next 100 years. And about 85% of people that currently live in such deltas might be at risk. This current estimate is about 14.25 million people. Deltas have also been experiencing severe flooding recently, with large areas experiencing submergence, and delta surface area might be increasingly vulnerable to flooding, or but new estimates may challenge these risk categories. Sorry, my computer is a little bit slow at the moment. I will have to, for a moment, stop sharing and sharing again.
No, you use the mouse, click that, you click that, yeah.
No, it's not advancing. So I'll just stop sharing for a second.
Yeah.
Sorry about that. So we've all probably examined this paper quite substantially, of which deltas are at risk. And the main conclusions from this paper that looked into a set of 48 deltas globally is that deltas are highly sensitive to increasing risks. And these come from local human activities, land subsidence, regional water management, global sea level rise, and climate extremes. Let me take you now on a tour of how I have experience studying deltas. And first, let me take you to Sacramento San Joaquin River Delta in California. And here you see a paper that was published in Science in 2007 that reflected many of the conflicts that we nowadays experience in deltas, not just in California, but in many other locations globally. And the hub of California freshwater systems is currently plagued by crashing fisheries, high demand, invasive species, and pollution. And in this specific location, earthquake that is overdue may devastate the state's drinking water and agriculture. They call this problem the Delta Blues California style. And a team of us, part located at the University of California, Davis, at the Center for Spatial Technology and Remote Sensing, together with many agencies at the state, including the California Department of Fish and Wildlife, have been studying what has been happening to the Sacramento San Joaquin River Delta over the last 18 years. And we first started by trying to understand what is the system and how has the Sacramento San Joaquin River Delta arrived to the state that it is together. We wrote a story that you can see in KQED Science, where we mapped the historical ecology of the delta and what kind of habitats have been transformed due to land reclamation and the very large process of changes in land uses over the last 200 years that led to the current delta that is a very restricted system that you see here on the middle picture, extremely levered, resulting from a lot of agricultural reclamation for land, and what is the current status of this system. So the Sacramento San Joaquin River Delta can be classified as a highly modified inland delta. It doesn't necessarily flow to the ocean directly. It goes through the Suisun March and the Bay Area before it actually reaches the Pacific Ocean. Due to this long history of reclamation and leveeing, it has resulted in a system that has a declining sediment supply like many deltas globally, decreased salinity, decreased suspended solids, declining primary productivity, and increases in toxic algae. The delta is characterized by many different types of environments that you can see here in the picture that have different tidal inputs, different freshwater inputs, riprap systems, a set of deep water chip channels that were built into the delta, a set of islands that were prior for agriculture and now have been inundated due to levee failure. And it also is characterized by counter-circuit flows. So you can imagine it's a very interesting case study to study delta development because it provides us with a wide variety of subsystems to examine. Bringing it back to the idea of the California blues, the Delta blues California style, it's very important to place it in the context of the state. California water politics are emblematic of the tension between conflict and cooperation. And these are two quotes that are very important to take into consideration when thinking about the Delta, because in California, it's said that whiskey is for drinking and water is for fighting. And at the same time, this conflict is counteracted by a cooperation that for this Delta, there are co-equal goals of water supply and biodiversity. So to get us back to how it all started with this fish. This is the Delta smelt, this is picture to scale with the fingers. There's a very small fish that entered the endangered species list because it had decreasing fish abundances. And once it entered the endangered fish list, it required that the state actually had to provide for habitat. This is a species that requires turbid habitat and slow waters. And therefore, major efforts were put forward to try to recover the populations of the Delta smelt. But the Delta has been experiencing changing landscapes. Here's a picture of submerged invasive species, Igeridensa, or Brazilian waterweed, and how it has been clogging the waterways of the deltas. Not only the submerged waterweed, but many other invasive species co-occur in the delta landscapes. And we were tasked to actually track invasion with imaging spectroscopy. Here's in the central picture, you see the extent of the delta. And for many years, we have collected information, first using the HIMAP spectrometer from 2004 till 2008. And now from 2014 all the way to 2018, we've been collecting imagery over the extent of the delta. So first, let me give you a little bit of an overview what is imaging spectroscopy to remind you what this technology is actually doing. So basically what we have is a very high spectral resolution. So we can collect very narrow, we can collect reflectance information over very narrow bands as depicted on the picture on the right, which allows us to identify not only major functional types and materials at land surface, but because of these narrow bands, we actually can differentiate between species, between functional groups, and I'll be showing you some of the results of how we actually use this technology to map the dynamics within this delta system. We also collected at 2-meter resolution, so very high spatial resolution allied with very high spectral resolution allows us to infer many processes of the ongoing changing delta landscapes. Together with the imaging spectroscopy, every year we collected over 2,000 field samples. Here's some examples for the years of 2014 and 15 that try to characterize the different delta life forms in terms of vegetation, being it submerged aquatic vegetation, floating vegetation, and emergent vegetation, also locations of water to obtain information on water quality, but also the dynamics of these plant communities. So what we found so far is that submerged species currently occupy 20% of the waterways. We developed several classification methods with accuracies over 90%. And you see here on the right hand side, some examples of the classification maps that we produce at this spatial resolution. We also examined how the herbicide treatment that is conducted to try to control this submerged expansion is working. And we find that specifically Brazilian waterweed tends to survive herbicide treatment because it has a very specific growth spurt in the fall. And therefore, the current state herbicide treatment efforts are hindered because of this physiological ability of this species, which makes this species outcompete other species within the plant communities. The other aspect about this species is that it actually disperses both radially and long distance, making the control of this species quite important and quite difficult. Why is invasion by this one species and the other species that occur in the different water columns within the delta matter? Well, it actually, this process of invasion and the other ongoing process of invasion affect system stability. We have been able to show that the increased cover by the submerged aquatic species is responsible for 20 to 70% of the sediment decline in the delta over these years of monitoring. It also changes sedimentation processes, reducing turbidity, which makes the delta smelt, the small fish that I started by showing you, more vulnerable to predation. We also see invasion by other species, such as the largemouth bass. And this largemouth bass is actually low turbidity adapted species. You see here in the bottom center a picture of the largemouth bass. They are very large predators, and their predation style is actually favored by the fact that submerged aquatic vegetation reduces turbidity in the waters, making smelt more vulnerable to predation. We also been able to monitor these processes over time. Here's some examples of areas that we've been monitoring submerged aquatic vegetation over the last times to see how does it actually change. And we see also through these analysis which areas are sources of invasive species and which areas are sinks where they decrease after a year. This is very important to understand how can we actually meet the goals of water supply and biodiversity protection. Largemouth bass, as I mentioned before, it's a key predator. And we also see that the largemouth bass is the recruitment, meaning the new juveniles that coming into the system are dependent on the density of submerged aquatic vegetation. So therefore, to manage for this endangered species requires managing the submerged invasive species as well as the other invasive fish species that co-occur in the system. We then use this information to look into how have the communities, their functionality changed over time. And we looked into, in this case, emergent and riparian communities to show that it's not just a systems change driven by changes in the submerged community, but we also see changes in functionality in the emergent and the riparian communities as depicted here in these four central plots. You see the top plots are the different traits space that emergent communities show in the decade of the 2000s, and the top right plot here, riparian in 2000, and then we compare it to the plots of the functional traits in 2010s for both emergent and riparians. What we see is a rearrangement of the trait space, and we attribute this rearrangement of the trait space to an increase in stress in this system. We have observed drought in the decades of the 2010s, and while in the system the hydrograph is controlled, other stressors might be changing leaf characteristics as depicted by the trait space change that we observe. We also see more water stress and more water salinity, which may impede photosynthesis and result in anticipated senescence. The presence of these invasive alien species, as I mentioned before, they might be more productive. That is a hypothesized reason for why they are so successful. But this is not so in the riparian zone, but it might justify what we see in the emergent zone. Further, if we think over time, emergent and riparian communities, they co-occur in the system at different points in times, and emergent tends to be more volatile, which might explain the differences between the two communities. And management and restoration, they have changed mostly riparian communities, which could contribute to the changes in the trait space that I've just presented. So getting us back to this idea of the co-occurring goals, you see that from an ecological point of view, there's several ongoing tightly coupled processes that co-occur in this very diverse delta system. Governance responses have been put in place to try to manage the changes in environmental systems. Sacramento's Joaquin River Delta management system consists of over 800 management entities that have a say over the different environmental components that make this system. Here's the picture of the network of these different management agencies, and the blocks, the squares, they represent main agencies that have most connections with other agencies that are involved in the management of this system. So what we see is actually that there are these central nodes, but they are not very strongly connected to many of the outer nodes that you see within this network. This suggests, this is the first point that I have in here, that strong bonding is absent. In a network where this governance structure would be functioning, you would expect not to see so many key players, but actually distributed players very well connected with all the management agencies that are responsible for this system. We also see that these strong governance institutions such as CalFed and the Delta Stewardship Council are just as important as the Department of Water Resources for coordinating the network activity. And we see a failure in including actors specializing in water politics that are not very active in the forums where decision-making is taking place. So I would like to get us to think about the social ecological lens for deltas. Let us bring us to then think about deltas as social ecological systems. What do I mean by deltas as social ecological systems? Taking the perspective that was proposed by Elinor Estrom, I consider a social ecological system as a coupled system where we have a subsystem that is ecological system. For the example that I just gave you, such processes of invasion and ecosystem services are part of ecological systems. And then there is a social system in parallel to this ecological system that has also processes where governance is also fundamental. So if we think about from this perspective, delta have resource systems that provide ecosystem services, which are harvestable resource units that historically have spurred human occupation in delta systems. The picture here depicts the major global populations and major global cities, and we see that the vast majority of the mega cities in the world are located in delta systems. And then what we see is that the favorable baseline conditions of deltas, they attract many users. The mega cities exemplify such attraction to many users and populations, but too many users may lead to resource units that are over-harvested, and the production of different types of ecosystem services that the delta provides may be undermined. Deltas are also related to other ecosystems, which might aggravate problems related to the delta resource system itself, and the wider socioeconomic and political setting may impose pressures from outside the delta that affect the management of the delta resource system and its interactions with the users' behaviors. Governance systems then have a role to manage these interactions between the social and ecological subcomponents. And to date, in deltas, these governance systems have often led to hard engineering types of interventions that may have decoupled important aquatic and terrestrial resource system functions. So with this in mind of what is social ecological system, given this conceptual framework, we did a little literature review of about 101 studies on delta systems to show which components within the social ecological systems have been most studied. This radar plot shows us that resource system and interaction between resource system and resource units, so the ecological subsystem, have been mostly examined in the literature, and also the interactions between resource system and the governance system. We see much fewer studies that focus on governance system and the users, and then the interaction between governance system and users, and the interactions between resource units and users. So let me take you now to a key conclusion from this paper on deltas at risk. So the current emphasis on short-term solutions for the world's deltas will greatly constrain options for designing sustainable solutions for the long term. So how have these knowledge that we have currently about delta systems, being it very local systems or globally, constrain options into the future? This gets us to the studies that we were conducting while I was at Utrecht University under the umbrella of the Future Deltas program, where we started to examine ideas for future deltas, but actually starting to look at them from a past perspective. We were interested in this idea of a delta Loctin. So a Loctin is, imagine that you are Apple product user, and you switch from one laptop to the next laptop, and you actually need to buy a new set of adapters for your new laptop. So a Loctin is when you're constrained in your choices because of your past choices. So we've examined this idea for deltas. And how we conceptualize this is that past changes in deltas could have led these systems to become locked in, and in our definition, unable or too costly to recover. And therefore, it would result in higher risks than those that deltas are currently facing. And how we conceptualize this, we looked into trends of population over time, but also on development of two types of land uses, cropland and irrigated land. And we conceptualized that a locked-in could be measured based on a correlation between population and cropland or population and irrigation. And when there is a lack of correlation or a decoupling between the development of population or either of the other land uses, we would be experiencing a locked-in. So we reconstructed the development of population and land use in this time for crop and irrigation for 48 major deltas over the last 310 years, using the history database on the global environment, which provide gridded estimates of land use change and population density over the Holocene. Here's a picture just of 45 out of those 48 major deltas that we actually examined. So let me give you a little bit of a rundown of the main results that we obtained. Here on the top picture, we see the population development over the last 150 years. And what we see is that over this time, global population grew about 6 times over this period of time. The bottom left picture shows you the population development over these 48 deltas. And what we can see is that population development is 10 times faster in deltas than in other areas. Here's a depiction of the growth rates of total population on the left picture, and in the middle panel, we see the growth rates just for deltas to compare to the global population growth. And we see that deltas show acceleration of growth rate, in particular over the last 50 years, and mainly in the deltas that are located between -10 degrees and 0 degrees latitude. What we also see when we examine the development of cropland in irrigation is that globally, so here the graphs are like the previous one. On the left, the growth rates of total cropland, and in the center, the growth rates of the delta cropland. We see globally a slowing down of land use change for croplands, but in deltas, we see no such no such slowing down. We see actually no change in land use change rates for cropland expansion. And we see very high cropland development in deltas situated between -20 and 0 degrees of latitude. Irrigation, again, globally, we see no differences with latitude. And in this case, for irrigation, it's the global north deltas. So deltas situated between 0 and 20 degrees north that show the higher increased irrigation expansion. And they also show an acceleration over the last 50 years. So then we took the land use development and we calculated 10% change from the original value in 1700. And the top row shows crop land use change, the middle row shows irrigation, and the bottom row shows urban land use change. And here you see the development of these different land uses in this set of 48 deltas globally. And then what we did was to look into how the relationship between population and cropland would change over time. So you see here the development over the last 150 years, and we calculated the correlation coefficient between the two properties. We see strong correlations between cropland and populations. And we see that options for change, meaning to change this relationship between cropland and population, are rapidly declining. And we see that for some deltas, Han, Nile, Pearl, and Cebu, maybe we already observe a decoupling between this cropland and population, inhibiting even further development in these deltas. We did the same for irrigation. We see weaker correlations than in comparison to the cropland. And actually, we could not find a trend related to irrigation. And this could be attributed to the fact that we actually observe more irrigation in the northern latitude deltas in comparison to the global south deltas. So then we took this information to define 3 types of Loctins. And here in the picture, you see the blue dots. They are deltas that we consider living deltas, meaning no Loctin, meaning that the correlation between the population, cropland, and irrigation development is still present in the way that we have defined it. And then we have two types of Loctin. Natural Loctin, when it's driven by crop or irrigation, or a social Loctin when it's driven by population development. And so what we see here, the triangles are locked in by natural processes, either agriculture or irrigation, and the black squares are driven by population development being faster than the development of crop and irrigation. And then we took a next step to look into how does these categorizations of delta Loctins actually compare with delta's categories of risk. So we took the categories of risk from the Tesler paper, and we compared these Loctin types with overall risk, which is a combination of risk to hazardous events, anthropogenic conditioning, and investment deficit, and also in comparison to relative sea level rise. So what we find is that these deltas that are locked in by either crop development or social development, they have higher risk. And then what we see is that for the other types of deltas, there are certain specific subcomponents of the overall risk that may matter depending on which kind of locked-in deltas we're referring to. Surprisingly, we also found risk for living deltas that is related to investment deficits. We then took this a step further. And now my PowerPoint has just a second. So we took this matching of Loctin with the risk categories a step further to try to examine how could, for example, ecosystem services or nature contribution to people contribute to decrease some of these risks. And this is some work with my current PhD student, Martin Rieder, here at the University of Zurich. So we then looked into how are nature contributions to people. So we took a wide variety of ecosystem services that have been modeled or mapped globally, and we extracted this information for these deltas. And here's the list of the ecosystem services that we actually considered. And then we map them to these categories of delta Loctin status. And what we find is that, not surprisingly, living deltas supply the most ecosystem services. They still have most of the higher values for all of these ecosystem services. Irrigation and social Loctin deltas provide the most food, and this is in line with what we would expect because irrigation promotes food production in many of these deltas. We also see that both living and social developed Loctin deltas supply the most biodiversity, but they also contribute most to invasive species. And in social Loctin, we have the highest pollination services. So the conclusions from this set of studies is that half of the analyzed deltas are currently in Loctin. They have lost resilience. We see that most are at risk of relative sea rise. And this is actually true also for living deltas, not just Loctin deltas. And many of them may have also lost nature contribution to people, in particular those that are Loctin due to cropland, but also irrigation. So together, this means that delta populations may be more at risk of hazards and decreased water supply, but these nature contributions to people may also be at risk. So we actually wanted to look into how can we implement governance structures that get us to resolve this conundrum of how deltas at risk can persist into the future. We looked into conservation actions that are currently conservation measures that are currently implied into deltas, and these include Ramsar Convention, the European Union Nature 2000, etc. But then we compared the risk trend as exposed by, as proposed by Tesler, with the percent of delta that is currently protected. So what we see here on the right-hand side panel is the risk factor ranked, and the same ranking for the deltas, but in terms of percent delta protected. We see no correlation between the risk and the delta protected, highlighting that new or additional conservation measures might be needed to think about how to protect the risks that the deltas might face into the future. So then we started to think about, okay, this is a nice subset of 48 deltas, but then what's the status of these ecosystem services globally? And this is a question for you. You all study deltas. How many deltas are there globally? I think there's very different types of estimates. You can tell me after in the Q&A session of what the answer is. One of the answers that I've seen is 1,800 when considering these different characteristics of deltas. We did not map all the 1,800 deltas, but we assessed 51 ecosystem services in 237 deltas worldwide, for which we conducted mapping of the delta extent, and we used measurements of ecosystem services as the one depicted here on the right-hand side picture. We then looked into how do these 51 ecosystem services bundle in global deltas. And bundle, we mean we define as correlations between different ecosystem services, and these correlations can be positive correlations when two ecosystem services are positively correlated, or negative correlations. The picture here shows you for all of the ecosystem services that we have been examining, the general patterns that we see in terms of the correlations. We see the most striking pattern is that biodiversity intactedness shows strong negative correlations with all the other bundles of ecosystem services. And these bundles include a bundle of productivity, a bundle of food, and a bundle of ecosystem services that relate with water processes. Here's the geographical distribution of these different ecosystem services supplies for all the deltas that we have examined. And you see some similarities that are aligned with biogeographical properties of the different deltas. So we see higher intactedness in the higher latitude deltas. We see more food in the mid-latitude and equatorial deltas. And we see higher dominance of productivity, ecosystem service provisioning in the southern latitude deltas. The geographical representation is for increased visualization, and it's not always the correct location of the delta. And then we explored how do these NCP supplies or ecosystem service supplies change with delta modification. We examined 4 human modification indicators: the population density, so that is the right top picture, the human footprint, the left top picture, flow disruption, the bottom left picture, and the human appropriation of net primary productivity, the bottom right picture. And then what we found is that there are actually some characteristic relationships between these 4 types of bundles of ecosystem services. Let me remind you: biodiversity intactness, productivity, food, and water, with these 4 indicators of human modification. And here's on the left-hand side, the picture of what the relationship looks like for all of the deltas that we examined. We then took this analysis, and we examined when, for which indicators actually each delta showed the worst relationships. And that's what the picture on the right-hand side shows you, is that we find that some deltas for at least 12 of these ecosystem services, these ecosystem services are no longer able to support the population densities that these deltas today host. So to conclude, this lens of deltas as social ecological systems, well, I started by showing you how resource units focusing on biodiversity, invasive species, and fish species, they are changing, and these biological communities are changing by many different processes. And over time, we actually can start to monitor how these resource systems in these constantly dynamic delta systems are changing. The users are also increasing and changing demands for natural and built infrastructure. However, we still lack quite a lot of information on the feedbacks from the environmental and the social systems to really fully understand deltas as social ecological systems. I've shown you an example of how we have used ecosystem services as flows between these systems, and we're really at the infancy to try to map which ecosystem services exist where, and we're still at the infancy to map them in terms of supply, and we're still missing information about the demand. We also examined how historical legacies could lead to lock-in systems and increase estimated risks for deltas into the future. And this is very important because governance systems in deltas need to deal with multiple goals, and future goals are becoming more inclusive and more diverse. And therefore, taking this social ecological lens might be necessary to understand all of the feedbacks that may take place in such complex systems as deltas. Deltas are also related to other ecosystems. They provide ecosystem services elsewhere, but they may also be affected by demands from elsewhere. And the overall socio-economic and political setting may put pressures that are external to the Delta system boundaries as we know it. So in conclusion, it shouldn't come as a surprise to you that deltas are in constant change. I showed you some examples of novel technologies and data that allow to assess change in deltas, and these are emerging, and more of these technologies are coming through to be able to monitor these, not just at the local scale, but at the global scale. We still need much more information on the feedbacks between environmental and social systems, and I hope that throughout this talk I've showed you how important it is to understand these feedbacks. And this gets us to this idea of seeing deltas as social ecological systems, and how can we use this coupled systems approach to understand the challenges that deltas face into the future. With that, I would like to thank you for your attention, and I think I'll take questions.
Perfect. Thank you very much. I really enjoyed it. I have some questions, but I'll if someone else in the audience has some questions, I'll let them go first. If you raise your hand or simply unmute yourself, you should be able to. If not, I'll go first and let other people gather their thoughts. I was wondering, Maria, how you determined the lock-in. I find it a fascinating concept. Are you locked in when you compete for space, or am I misinterpreting it?
Yes, so you could phrase it in that way, that at some point, because you have to choose either to go urban or to go to other land uses, whatever you choose will reduce your ability to choose into the future.
Okay. And then so sea level rise or like diminished delta extent might increase the chances for a lock-in.
Yeah, exactly. Or a system that now is kind of at the verge, because there's a few of them that we identify that they are not yet there, but if they decrease in area, they may create more competition for land.
Okay.
Maria, I think this is a fantastic talk, because in this River and Delta talk series, we talk mainly the natural process, but now the social ecological perspective is exactly what we need. It's very important. You give us a very interesting angle, look at the risk of the global river delta. And look at the list you showed all the risk. You see the long list. On the top one, on the top 10 almost is the South Asia deltas, like all the way from Godavari, Indus River, Ganges, Irrawaddy, Mekong, almost, over there. So have you compared those to a population density?
Let me go back. They were in our analysis. So here's the population development. Can you see it now, or you need to share?
Yes.
So you see, so some of them, they are just not organized by latitude, they are organized by alphabetical order, sorry. But you do see here the different developments for those 48 deltas. So we did look into them, but they do, so Mekong, Mahakam, some of the Indus, they have some of the steepest population developments that you see in there. And most of them actually came in to become locked in because of the social development that outpaced.
Yes.
Population development outpaced the land use change into agricultural areas.
Can you go to the slide? Then you have a a vertical list of the risk, the R value.
Yeah, I can. Let me just. I don't know about you, but my computer every time I have to give it off this.
This one. Looks like the human population increase rate. Of course, the demand is cannot catch up the natural adaptation, and because the delta is have its own way to respond the sediment reduction in sea level rise subsidence, but the increased population, the rate is so high, so quick, and is kind of the system sometimes is not sustainable. And so like the Mekong River, like all the Indus or even Ganges, Irrawaddy, and in Mississippi River is still population still high, but somehow, I know it's better or not, I don't know, but it's still a challenge.
No, I would fully agree. And so that's why we decided. So when we started examining this Loctin, we were like, okay, so what could be factors that could lead to the Loctin? And we say, okay, it could be the development of the agricultural land uses, but it could be the population as well. And both of them have very different processes. And if we're thinking about like governance, they will be very different governance systems if you're thinking about population goals versus agricultural land attribution. And that's why we started looking into the ecosystem service provisioning. So are these populations still depending on ecosystem, or could they still depend on ecosystem services, because these are also massive deltas, and maybe the populations could be concentrated but still be able to subsist out of what deltas, or do they require a lot of imports of exports? So for example, the Mekong Delta is shown to be related a lot with rice production for elsewhere. So where do we actually think about? We haven't even touched the trade aspect. So we see for the global deltas with the ecosystem services that there are systems that persist despite the level of ecosystem services that they are able to produce and supply. That means that they are importing ecosystem services from elsewhere, or they are doing some sort of trade-off between exporting some and importing some others. And so those processes is what we actually don't know exactly for all of these deltas globally, because we only start now to have some data sets on trade and how much gets exported from elsewhere. So we're just really now making an assumption that, okay, what is produced within this physical area is what is available, but actually we know that there's trade in there as well. So we show that for some of these systems, they can only subsist based on trade. And so the question is, for how long?
Exactly.
So I had a question related to that. So with all the data you have on the ecosystem services, can you estimate how important deltas are to the rest of the world not living on deltas? Because if the Mekong would drown and the Ganges and like that would have global importance.
That's one of the things that we're thinking of starting to examine right now, and it's, I think there's a wealth of questions that actually we could answer with that data set of really getting to this idea of, we're just really at the beginning of what is the risk and how is this risk that was first estimated for these 48 deltas escalated by the fact that they are locked in, but also by the fact that deltas actually are major exporters of services to other locations. So that will create additional pressure. So this is the part of like the interactions with external ecosystems, but also from elsewhere into the delta. So we are starting to conduct a survey in some of these deltas to know what people actually within the delta use and what the deltas export. But that is an excellent question to
very good. For example, in China, the Yangtze in Shanghai, Shanghai, the Yangtze area, and also the Pearl River, Guangdong, Shenzhen, Hong Kong area. that could be up to 30 or 40% of the whole China GDP. I mean, that's two delta added together, even like a Dhaka in the Bangladesh. So I think it's very interesting. Sorry, I stop here. So is any other people have any question?
Well, but that question is the same that we have with California, right? So this delta
California
is a huge contributor to US GDP. And so it exports a lot of the products that it produces actually not to stay in California, it's for elsewhere. So the question that Yap just asked is like, so how much do deltas contribute to food security or water security elsewhere is a very important question.
Very good.
So I don't think others are going to have questions. Well, I'm just going to ask one more question. I'm fascinated with all the data you showed. So you have this high data set that has timelines or time series of these data. Do you have an estimate of, I guess it's a two-part question. Do you have estimates of when deltas started to become locked in? And do you have examples of deltas that got out of it?
We examined 300 years. For all of the European deltas, they were locked in before that.
Okay.
We can say that. Deltas getting out. So yes, in the paper, we do it by time series, and we actually see when the deltas actually start to become locked in. I don't have out of the top of my mind an example out of those that became and not, but in the paper we have that specified. And then the ones that came out, I don't think we found any example that came out yet out of that.
Interesting.
Not too comforting.
Yes, it's not too comforting, but I think that that is also a main point. Is like, okay, so 50% of them, based on this categorization of locked in, could be locked in, so they could be more at risk, and then we need to think about how could we actually invert this. So that's why we started to look into conservation. Would conservation areas actually match the risk factors? And we see in this slide here that basically the area that is protected by delta has no relationship whatsoever with the risk of the delta. And then we thought about ecosystem services, because in the ecological theory, we know that ecosystem services could provide an insurance to respond to some of these risks. And so this gets to the question of, if ecosystem services could provide really the insurance, then maybe it would be a way to get out of this locked in status. But if they are exporting these ecosystem services, maybe they are actually exacerbating this locked in status.
One more thing, Maria, maybe this is, if you think about the crops, the rice production, and I'm not sure you have the historical data or not. If you look at a couple major that kind of rice bowl, like a Mekong, like the Ganges. So I predict, I haven't seen any data yet. I predict the production will maybe already reach a platform. That means there's a threshold for the maximum that delta can produce. But that maximum maybe begin to decline because of subsidence, saltwater intrusion, or storm. I don't know. I don't have data. Just something in my mind. I feel that way. But can you collect the data to demonstrate? That would be a very interesting thing to show.
That would be my ideal data set. That's why we started with HIDE. Like, these longitudinal data sets are very few and far in between. So right now we're doing this space by time substitution with ecosystem services, because we really don't have longitudinal data set to be able to do that. So either we use some sort of cost development model to estimate how it would develop for the Mekong, but we would need a lot of data that it's currently, to my knowledge, not available, or even collect at the granularity that we would need. I have a lot of ideas of data that we would need, really.
Okay, cool. Maybe next project or next paper. Okay, interesting. Maybe,
right.
We can stop here, maybe.
Yes, yeah. If there's no one else, then thank you again, Maria, for your talk, and we should chat at some point. on
Yes.
all the data you have and all the data that I have and want. So, perfect. All right. Thanks again.
Thank you.
And hope to see you all next week.